So hello and welcome back. So we have another question over here. We want to find the derivative of f of x is equal to 3. We want to find the derivative of f of x is equal to 3 at x is equal to 0. X is equal to 0 and at x is equal to 3. So basically the first thing that you see over here, your function is a constant function, meaning that it's a horizontal line. And so if you have 1, 2, and 3 over here, this would be the graph of your function. F of x is equal to 3. And of course it's a straight line, a horizontal straight line. And so the slope of a horizontal straight line at any point is equal to 0. That means that the derivative of this function at any point, either at x is equal to 0 or at x is equal to 3, if you calculate that, that would be equal to 0, because basically because again the slope of a straight line of a horizontal straight line at any point is equal to 0. But we can try and you will get basically, and the solution basically over here says that since the derivative measures the change in function, intuitively it's clear that the derivative of the constant function must be 0 at every point. This is indeed supported by the following computation. So the computation basically we said that f prime of a is equal to the limit of basically f of a plus h minus f of a over h as h tends to 0. So the derivative of the function at some point a is equal to the limit of f of a plus h minus f of a over h as h tends to 0. So now if for example, suppose that your a is equal to 0 here. So then f prime of 0 is equal to the limit of f of 0 plus h minus f of 0 minus f of 0 over h as h tends to 0. As h tends to 0. Now this is f of 0 plus h is equal to f of h, so this is the limit of f of h minus f of 0 minus f of 0 over h as h tends to 0. Now you know that f of h is basically in the case of this function is again the same thing, is equal to f of x, because you have no variable here, so you get basically at any rate you get 3 over here, so you get a limit of basically 3 minus, now f of 0 again is the same value 3 at over 3 basically 3 minus 3 and then over h as h tends to 0, and this is the same thing as the limit of this is equal to the limit of 0 over h as h tends to 0, which is equal to 0, because this is 0. The value of this function is equal to 0. So the limit of 0 when h tends to 0, or when h tends to any a basically, is equal to 0, of course, the value of the function. And if you calculate, for example, f prime of 3, for example, if you calculate f prime of 3, that would be basically again the limit of f of basically 3 plus h minus f of 3 over h as h tends to 0. So again, the function that we had was basically f of x is equal to 3. So f of 3 plus h, f of 3 plus h is again basically the same as the function itself, which is equal to 3, because I have no variable here. And again, f of 3 is again the value of the function 3 over here. So that doesn't make any difference. So again, you will get the limit of basically 3 minus 3 over h, minus 3 over h as h tends to 0, which is again the limit of 0 over h as h tends to 0, which is equal to 0. So you can see that the slope of a straight horizontal line, the slope of a straight horizontal line at any point is equal to 0. Now, what we have here now is we now present a geometric interpretation of derivative of a function at a point. Let y be equal to f of x be a function, and let p a comma f of a and q another point a plus h, f of a plus h be 2 points close to each other on the graph of this function. So the figure 13.11 is now self-explanatory. So the figure that we have is basically this figure over here. So we have, it's basically the same situation, essentially the same situation that we discussed before. This is the x-axis, this is the y-axis, and this is your function. And this is your function. And you have, for example, some point A over here. You have some point A over here. And you have some point A plus H over here. And this point, you can call it P, for example. This point, you can call it Q. So the coordinates of this point would be a comma f of a, and the coordinates of this point would be a plus h comma f of a plus h. And so again, this would be this point over here would be f of a plus h. This point over here would be f of a, and I can call this, and basically the function itself, I can call it y is equal to f of x. Now, at this point, I can draw a tangent to this function, which would look something like this. which would look something like this. Suppose that this is a tangent at this point to the graph of the function, and the tangent goes through the, basically makes an angle of psi, makes an angle of psi with the positive direction of the x-axis. Makes an angle of psi with the positive direction of the x-axis. And of course, this distance over here is naturally then h, and this point, for example, I can call it r, and that's basically the situation. I can call this point O, for example. Now, so now we know that basically f prime of a is equal to the limit of f of a plus h minus f of a over h as h tends to 0. F of a plus h, which is basically this value over here, minus f of a, so that's the distance between these 2 points, over h, which is the distance between these 2 points. And if you take the limit of this ratio as h tends to 0, that would be the derivative of the function at point A, basically. Okay, so now about this situation, you can see that basically so we know that f prime of a, as we saw before, it was f of a plus h, which is basically this point over here on the y-axis, minus f of a over h, which is basically this distance over here, the difference between a plus h and a, as h tends to 0. That was the derivative of the function of this function at x is equal to a. Now from this triangle PQR, from this triangle over here, you can see that the ratio whose limit we are taking, the ratio is basically, we have the ratio of QR to PR, basically we are taking the limit of this ratio. So the ratio whose limit we are taking is precisely equal to tan of QPR. So tan of basically QPR is this angle over here, and if you take the tan of this angle, it's going to be the opposite by adjacent, and so of course you know that tan of QPR, angle QPR, is equal to QR divided by PR, which is incidentally equal to f of a plus h minus f of a over h. So this is the ratio, and this ratio is basically this this ratio over here, which is equal to tan of QPR, tan of this angle, and we are basically taking the limit of that ratio, which is basically the slope of the chord PQ, the slope of this chord. So this is also equal to the slope of the chord PQ. Now in the limiting process, as h tends to 0, meaning that as this point gets closer and closer and closer to this point, the point Q basically tends to the point P, and so the limit of, and so you can say that the limit of basically QR to PR, the limit of QR to PR as Q tends to P, is the same thing as the limit of basically f of the same ratio over here, f of a plus h minus f of a over h as h tends to 0. Now this is equivalent to the fact that the chord PQ tends to the tangent at point P of the curve y is equal to f of x. So this is equivalent to the fact that this chord PQ tends to this line segment, to this line that I have drawn over here, which is tangent to the function at point P, to the function basically y is equal to f of x. And so the slope of this line, and so you can say that basically, of course, you know that the limit of QR to PR as Q tends to P, or the limit of f of a plus h minus f of a over h, basically this limit, that is equal to the slope of this line, which is tan psi. That means that you can write f prime of a is equal to tan psi, So that means that tan psi is actually the value of the derivative of this function at point A. That's basically all that it means. Now for a given function f, we can find the derivative at every point. Of course, with the same kind of process, we can find the derivative of the function at any point. So it seems that we have no problem for doing that. And if the derivative exists at every point, if the derivative does exist at every point, then it defines a new function called the derivative of f of x. So suppose that for every input over here, which is some a, you will get some output over here. So for example, for this input a, you have gotten tan psi. For another output over here, you will get tan of some other angle over here, and for another input, you will get the tan of some other angle, and so on and so forth. And so when you put those points together, you will get a new function, which is simply a function which is the derivative of this function at every point in the domain of the definition, wherever basically this limit is defined. So formally we define the derivative of a function as follows. So then basically logically then we can say that suppose f is a real valued function. Suppose f is a real valued function the function defined by the function defined by the limit of f of x plus h minus f of a over h as h tends to 0, this function, and we already understood what that means, what we mean by that function. Wherever the limit exists, is defined to be the derivative of so basically wherever that the limit exists is defined to be the derivative of f at x, and is denoted by f prime of x. Okay, so it's denoted by f prime of x. So let me I did make some mistake over here. Is denoted by f prime of x. So this definition of derivative, okay, so we said that basically as a definition, we said that suppose f is a real valued function, the function defined by the limit of x plus h minus f of a over h as h tends to 0, wherever the limit exists, is defined to be the derivative of f at x and is denoted by f prime of x. Now this definition of derivative is also called the first principle of derivative. The first principle of derivative. The first principle of derivative. So you can say that f prime of x is equal to the limit of f of x plus h minus f of x over h as h tends to 0. So that is the definition. Now, clearly the domain of definition of f prime of x is wherever the above limit exists. So clearly the domain of definition of f prime of x, the domain of definition of f prime of x is wherever the above limit exists. There are different notations for derivative of a function, so the different notations that you can use the different notations that you can use. Sometimes you use, for example, the f prime of x. Sometimes you use d by dx of f of x. Sometimes you use, or basically if y is equal to f of x, then you can say dy by dx. And this is basically referred to as the derivative of f of x, or y. This is referred to as the derivative of f of x or y with respect to x. And it can also be denoted by d of f of x. Also, there is some other notation that you need to be familiar with. The derivative of f at x is equal to a. The derivative of f at x is equal to a. So the derivative of f at x is equal to a is denoted by d by dx of f of x at x is equal to a. You can write it this way, or you can write it as df by dx, at x is equal to a, or you can even write it as df by dx at x is equal to a. So these are the different notations and different things, but now basically we understand what the whole thing actually means. So now let's do a couple of examples to understand these a little bit better, and then we will. So you want to, for example, find the derivative of f of x is equal to 10x. Suppose you have f of x is equal to 10x. Now we said that f prime of x is equal to the limit of f of x plus h minus f of x over h when h tends to 0. So then basically what you can write basically in this function, f of x plus h is going to be equal to 10 times x plus h, which is equal to 10x plus 10h, and f of x, you already know what that is. So then the f prime of x is equal to the limit of f of x plus h, which is equal to 10x plus 10h minus f of x, which is equal to 10x over h when h tends to 0. And so 10x and negative 10x you can cancel out, h and h you can cancel out, and you have the limit of basically 10 as h tends to 0, which is equal to 10. and of course, if you take a look at this function, f of x is equal to 10x, for example, it's going to be some function like this: 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10. And so you will get this point over here, and your function goes through the origin and this point. So this is f of x is equal to 10x. So what that means is that you can see that the slope of this line, this is a straight line with a slope 10, meaning that, of course, since it's a straight line, at any point on the I mean, or you can say between any 2 points on the line, if you calculate the slope of this line, you're going to get the slope is going to be equal to 10. And I've gotten the derivative of the function as the same number 10. So that means that what that means is that at any point the slope of this line is 10, and it's not changing because then basically because it's a straight line, and of course in the case of a straight line the slope is never changing. And so if you want to basically draw the graph of this function, is going to be the slope of the line. So this is f of x is equal to 10, which is the derivative of this function over here. The derivative of this function f of x is equal to 10x would be g of x is equal to 10, and this function now is the derivative of this function of this function over here. Or suppose that you have the derivative of, for example, f of x is equal to x squared. So the derivative of f of x is equal to x squared, we said that f prime of x is equal to the limit of f of x plus h minus f of a over h as h tends to 0. So basically f of x plus h is going to be x plus h whole squared, which is the same thing as x squared plus 2hx plus h squared. And of course this is supposed to be f of x, I'm sorry. So I can write this as the limit of basically f of x plus h, which is equal to x squared plus 2hx plus h squared minus f of x, which is minus x squared over h as h tends to 0. And these two you can cancel out, and you can write this as the limit of basically h times 2x plus h over h, and these two you can cancel out as h tends to 0. And so in the limit you will get basically the limit of 2x as h tends to 0, 2x as h tends to 0 plus the limit of h as h tends to 0. So of course this is going to be equal to 0, and this is going to be equal to 2x because h is simply not present here. So this is going to 2x plus 0, which is equal to 2x. So that means that if you have a function f of x is equal to x squared, then f prime of x is going to be equal to 2x. And what that means is that the slope of this function at any point is equal to 2x, meaning that if you have the function over here, f of x is equal to x squared is going to be some function like this. Now if I draw the line, for example, this is f of x is equal to x squared. Now if I at x is equal to 0, for example, the value of this function becomes 2 times 0, which is equal to 0. So then at this point you will get, for example, this line over here, which is the x-axis, which is tangent to the function at this point over here, and is basically the derivative of the function, or the slope of the function at this point. At point, for example, I don't know, 1, for example, suppose that you have at this point 1 and 1, and then your function goes through this point, and at 2 it goes through 4, for example, 1, 2, 3, and 4, so it would be something like this. At 3, for example, you would end up at 9, so 1, 2, 3, 4, 5, 6, 7, 8, and 9. 1, 2, and 3, 3, 9 would be some point over here. And the same thing happens over here. The same thing, because the function is supposed to be symmetric. Now, what happens is that, for example, at this point x is equal to 1, you see that the value of the derivative of the function is 2. So that means that at x is equal to 1, basically what that means is that basically the slope of the function at x is equal to 1 is equal to 2. Let me see, for example, f prime of x f prime of, for example, 1 would be equal to 2 times 1, which is equal to 2. So at this point x is equal to 1, the slope of the line is going to be 2. So you would get some basically some point over here, and 1 and 2 somewhere over here, so you would get some line like this. At, for example, x is equal to 2, f prime of 2 is going to be equal to 2 times 2, which is equal to 4. So that would be basically this point over here, and 1, 2, 3, and 4, you would end up somewhere over here, so you would have this line over here. Now we can actually see this. On a graph much better. If f of x is equal to x squared, suppose that f of x is equal to x squared. Now, for example, at x is equal to 1, if at x is equal to 1, suppose that the slope of the function is 2, m is equal to 2. Now, so f of x is equal to mx plus c. it's supposed to be a line passing through it is supposed to be a line passing through this point P, whose x coordinate is 1, whose y coordinate I don't know, but then I know that the slope of the line is I know that the slope of the line is 2, meaning that y2 minus y1 over x2 minus x1 is equal to 2, and one point over here, I already know about this point. One point over here, I already know. It's basically x is equal to 1 and y is equal to 1. 1 comma 1. And the slope is 2. This is equal to m. So y is equal to mx plus, or I can write y minus y1. Y minus y1 is equal to m times x minus x1. So I can write y minus 1 is equal to 2 times x minus 1. So y minus 1 is equal to 2x minus 2, or y is equal to 2x, and negative 2 plus 1 is negative 1, 2x minus 1. Y is equal to 2x minus 1. So if I draw this line over here, f of x is equal to 2x minus 1, and you can see that the line is exactly tangent to the function at this point 1 comma 1. Now for example and this is actually the derivative of the function at this point 1 comma 1. Now suppose for example at x is equal to 2, the value of the function is 4. So 2 comma 4 is, so 2 comma 4 is basically another point on the graph of the function, 2 comma 4. Now based on the derivative, I know that basically the f prime of x is equal to 2x. So when x is equal to 2, f prime of 2 is going to be equal to 2 times 2, which is equal to 4. So this is the slope of my line. So my m is equal to 4. So again, y minus y1 is equal to m times x minus x1. So y minus 4 is equal to 4 times x minus x1, which is equal to 2. So y minus 4 is equal to 4x minus 8, or y is equal to 4x negative minus 4, 4x minus 4. Now y is equal to 4x minus 4 would be this line over here. So f of x, or g of x, is equal to 4x minus 4. And you can see that exactly at this point over here, which is exactly at this point here, 2 comma 4, this green line over here is tangent to the graph of the function, and that means that basically the slope of the function at this point is equal to 4 actually, because this is the slope of the line, the slope of this line, which is tangent to the function at this point. And in the same way, you can find an infinite number of lines tangent to this function at all the infinite points that there are on the graph of this function. Okay, so that is that. So that's basically the meaning of the derivative of function, meaning that what it means for a derivative of the function is basically, suppose that you can imagine that this function, let me hide these. You can imagine that this part over here is the position function. This is, suppose that this is the position, this axis is the position, and this axis is the time, related to that stone that we talked about. So now this stone has this kind of basically function over here, and this is the position function of that stone. Now this, so based on this rule, that stone is changing its position with respect to time. Now, at different points in time, the instantaneous velocity of the stone is changing. It's getting basically, it seems that it's getting faster as we move along here, because, for example, the slope was 2 over here, the slope was 4 over here, and so on and so forth. So what that means is that then if I draw, for example, if I draw this line tangent to the function at this point, what that means is that exactly at this point in time, the stone is behaving like a stone that is which is changing its position with respect to time, whose behavior can be exactly at this point can be modeled using a linear function, meaning that using this linear function, and then at the next point, for example, at x is equal to 2, then you can say that then the behavior of the stone changes. At that point, the behavior of the stone, or the way that it changes position with respect to time, can be modeled using this linear basically model, and so on and so forth. And basically, when you put all of these functions together, I mean, basically using this relationship that we found over here, which was basically f prime of x is equal to 2x, then using this we can calculate the slope of that, the slope of the graph of the function, or the graph of this function, for example, at any point in time, or at any point x basically. Okay. Now suppose that you have another function. Suppose that you have another function Okay, so now suppose that you have a function, you have a constant function f of x is equal to some constant or a fixed real number a. For example, f of x is equal to a, some a basically. And basically this function would be something like, for example, f of x is equal to 3. And of course you know that for example, if you had f of x is equal to 3, your function would be something like this. And you know that the derivative of basically the slope of this line at any point on the line is basically 0. So then you can simply say that f prime of x is going to be equal to 0 if f of x is equal to a. if f of x is equal to a. So now, in order to basically calculate that using the definition, what we can do is that basically we know that f of x is equal to a, and we said that f prime of x is equal to the limit of f of x plus h minus f of a over h as h tends to 0. And that is equal to basically f of x plus h. In the case of this function, if your function is f of x is equal to a, so over here you have basically no variable in your function. So then based on this, f of x plus h is going to be the same thing as f of x would be the same thing as basically a. And of course f of a is going to be this is supposed to be f of x. So f of x, you already know what that is, so we can calculate it. So then I can write f prime of x is equal to the limit of basically f of x plus h, which is equal to a, minus f of x, which is equal to a, over h as h tends to 0. As h tends to 0, and that's the same thing as the limit of 0 over h as h tends to 0, and I can write this as and of course this is going to be equal to 0 as h is not equal to 0. As h is not equal to 0, then this is going to be equal to 0. So then you can see that the derivative of your function at any point, really, because there is no variable here, at any point is going to be equal to 0, which means that the slope of a horizontal straight line is 0, basically, at any point on the graph of the function. Okay, so then the next thing that we have is we want to find the derivative of f of x is equal to 1 by x. F of x is equal to 1 by x. So you know that the function f of x is equal to 1 by x is basically some function like this, if I'm not mistaken. We will check that, of course. Some function like this. So if you have f of x is equal to 1 divided by x, we can see that the function is basically something like this, meaning that the x-axis and the y-axis are both the horizontal and the vertical asymptotes of the function. Now, the derivative of this function is going to be f prime of x is equal to the limit of f of x plus h minus f of x over h when h tends to 0. So so then you can say that the derivative of the function is the limit of f of x plus h, which is basically 1 over x plus h, 1 over x plus h, minus f of x, which is equal to 1 over x, over h as h tends to 0. And the way that you can solve this problem is probably you can write this as, I think, the limit of basically x times x plus h, x times x plus h, and you get 1 minus x over h minus x, and then as x as h tends to 0. And so I can write this as let me see. I think I made a mistake over here somewhere. Let me see. So if I write this as x times x plus h and divide this whole thing by this denominator, you will get x, and divide this by this, you will get x minus h, x plus h over h as h tends to 0. And this is the same thing as the limit of basically x minus x is equal to 0, so that's a negative h. That there you would have a negative h over x times x plus h over h as h tends to 0, which is equal to the limit of basically this negative h over x times x plus h times 1 over h as h tends to 0, and then h and h you can cancel out, so you will get negative 1 over x times x minus h. You will get negative 1, you will get the limit of negative 1 over x times x minus x plus h as h tends to 0, and then what you can do, okay, so if I write this as the limit of h tends to 0 of negative 1 x squared plus hx okay, so then you can write this as the limit of basically negative 1 over well, when h tends to 0, this becomes 0, and you will get negative 1 over x squared. we will get negative 1 over x squared. And that's the limit of your function. I'm sorry, the derivative of your function. And again, you can basically test this. For example, suppose that your function is f of x is equal to 1 over x. Now f prime of x, we found it to be negative 1 over x squared, which is of course one of the formulas that we will learn soon. Now the graph of the function, as we saw over here, is basically this graph over here. Now at x is equal to 1, for example, you can see that the output of the function is 1. At x is equal to negative 1, the output of the function is negative 1. Now at these 2 points, for example, at x is equal to 1 and at x is equal to negative 1, you basically, the derivative of the function is going to be at a straight line tangent to the function at this point, and it seems to be a line having the slope negative 1 passing through this point 1, 1. So 1, 1 is basically 1, 1, 1 is 1 point on the graph of the function, and the slope of the line at this point is going to be f prime of m at this point. The slope of the line is going to be f prime of 1, which is equal to negative 1 over 1 squared, which is equal to negative 1. Which is exactly what I just said, that it's a line passing through this point and having a slope negative 1. So y minus y1 is equal to m times x minus x1. Y minus y1 is equal to 1 is equal to negative 1 times x minus 1. So y minus 1 is equal to negative x plus 1. And so y is equal to negative x plus 2. Now negative x plus 2 is going to be equal to this thing over here. F of x is equal to negative x plus 2. And you can see that it's a line tangent to the function exactly at this point 1, 1, having a slope of negative 1. And we can find the other point over here as well. For example, if you take the point negative 1, 1, if you take the point, for example, negative 1, negative 1, I suppose it was negative 1, negative 1. Again, it's a line that passes through the function at this point, and the slope of the line is f prime of negative 1, f prime of x, which is equal to the slope of the line at that point. So that is equal to basically negative 1 over negative 1 squared, which is equal to, again, negative 1. So now y minus y1 is equal to m times x minus x1. So y minus, so minus negative 1 is plus 1 is equal to negative 1 times x plus 1 again, because it's a negative 1 over here. So then y plus 1 is equal to negative x minus 1, or y is equal to negative x minus 2. So now y is equal to negative x minus 2 is going to be a line over here. Y, or f of x, is equal to negative x minus 2. And you can see that it's a line touching the graph of the function exactly at the point negative 1, negative 1, which is the which is the exact slope of the function at that point, which is the derivative of the function at that point. Okay, so I'm going to end this video here, and then in the next video we will talk about the algebra of derivative of functions. I'll see you in the next video, and thank you.